Good evening, everyone. Let's just wait for 5 minutes so that people can join. Okay, so let's start. I hope you all must have gone through the lecture videos of this week, and you all must be aware about the power series solution of second order differential equations. So today we'll be solving some problems related to power series solutions. So let's start with the first question. Find the singular points and nature of singularity of the differential equation x square x minus 2 square double derivative of y plus 2 x minus 2 y dash plus x plus 1 y equals to 0. Let's number this equation as equation 1. So we need to find the singular points and their nature. What do we mean by singular point? So for a differential equation of the form y double dash plus p1x y dash plus p2x equals to 0, singular points are the points where these functions p1x and p2x are not well defined. So if we convert the given problem, the given equation 1 in the standard form, we call it the normalized form. So in normalized form, first can be written as can be written as y double dash plus c. We'll just divide the equation by x square x minus 2 square. So now since we already have x minus 2, we are left with x square x minus 2 y dash plus x plus 1 y by x square x minus 2 square is equal to 0. So here our p1x is, this implies our p1x is 2 by x square x minus 2, and p2x is x plus 1 by x square x minus 2 square. So we know that these two functions are not defined at x equals to 0 and x equals to 2. So the two singular points that we have for our problem are 0 and 2. This implies singular points for equation 1 are 0 and 2. Now next we need to find the nature of singularity. So to discuss the nature of singularity, we'll first see, uh, let's start with the singularity x equals to 0. X equals to 0. So let me start with the definition. Let's recall the definition. Recall, A is said to be a regular singularity if x minus a px and p1x x minus a square p2x both are analytic at x equals to a. Now we'll see what happens in our problem. So let's see with x equals to 0. Now x p1x is 2x by x square x minus 2, which is 2 by x minus 2. Now this is not analytic at 0 because clearly it's not even well defined at x equals to 0. Not analytic at x equals to 0. Therefore, okay, let's see what do we have. X square p2x. There we have x plus 1 by x minus 2 square. Even though this is analytic, but for regular singularity, we need both of them to be analytic at x equals to 0. Therefore, x equals to 0 is an irregular singularity. Is an irregular singular point. Next we have x equals to 2. Now let's see, x minus 2 p1x is equal to 2x by x square, which is 2 by x. Clearly this is analytic at x equals to 2. We don't have any kind of singularity at x equals to 2 for x minus 2 by x minus 2 times p1x, and x minus 2 square p2x is x plus 1 by, what was p2x? X plus 1 by x square. Again, this is also analytic at x equals to 2. This gives us that x equals to 2 is a regular singularity. Therefore, x is equal to 2 is a regular singular point. I hope you all were able to see how we are finding the singular points and then justifying their nature. Okay, then let's move to the next question. Question number 2. Find the power series solution of find the power series solution of y double dash plus xy dash plus x square plus 2y equals to 0. Let's number this as 1 in terms of in powers of x. Now see that this equation 1, clearly x equals to 0 is an ordinary point for this problem, for this equation. We don't have any kind of singularity at x equals to 0. So we have a result that if x naught is a ordinary point, then we have a power series solution for that equation near that point. That means we have a power series solution near 0. That means, let me write it, since x equals to 0 is an ordinary point, this implies there exists a power series solution for one near 0. So we can take y x equals to summation n from 0 to infinity cn x to the power n. So all we need to find are these coefficients cn's. So once we have the value for cn, we can find the solution. So now since this y is a solution, we'll just differentiate it once and twice and then put that again in back, substitute these values back to the equation 1, and then by comparing the coefficients of various powers of x, we'll find the value of the coefficients c. So let's see. Let's just start. This implies y dash x is equal to summation n from 0 to infinity n cn x to the power n minus 1, not 0 to infinity, 1 to infinity, and y double dash x is equal to summation n from 2 to infinity n n minus 1 cn x to the power n minus 2. Now substituting y dash and y double dash in first, we get what we get. So we'll get summation n from 2 to infinity n minus 1 cn x to the power n minus 2 plus summation n from 1 to infinity n cn x to the power n minus 1 sorry, n plus summation n from 0 to infinity Cn x to the power n plus 2 plus 2 summation n from 0 to infinity Cn x to the power n equals to 0. We have just substituted these values in equation 1. So now we'll try to make these sums bit in such a way so that we can dis- distinguish coefficients of x to the power n. So, our main aim is to make all these powers same. So we'll just use substitution method. Let's start with the first term. Now summation n from 2 to infinity n minus 1 Cn x to the power n minus 2. We want it to be something summation some coefficient x to the power m. So let's take m to be n minus 2. So we get m for n equals to 2, m is 0, m from 0 to infinity, and the coefficients would be n is now m plus 2 and n minus 1 will be m plus 1. So similarly, okay, we have c also, no? So c m plus 2 x to the power m. Similarly, summation n from 1 to infinity n c x to the power n can be written as summation m from 1 to infinity m c m x to the power m. Here we have just substituted n by m so that our equation becomes a bit normal. Next we have summation n from 0 to infinity Cn x to the power n plus 2. It can be written as summation m from 0 to infinity Cm x to the power m minus, sorry, this is m from 2 to infinity m minus 2 x to the power m. So now we'll be writing our equation 2 in the form of summation of m. So this implies equation 2 becomes, so the first term was summation m from 0 to infinity. Now our sum is carried on m plus 1 m plus 2 m plus 1 2 x to the power m plus summation m from 1 to infinity m c m x to the power m plus summation m from 2 to infinity Cm minus 2 x to the power m plus 2 times summation m from 0 to infinity Cm x to the power m equals to 0. All we have done is just made the sum, written the sum in such a way that we have the terms x to the power m everywhere. Now we can see that in some of the terms the sum is starting from 0 and some from 1, somewhere from 2. We'll try to make this all this uniform and take the terms. For example, in the first series, I'll take the first two terms, and then the rest of the sum would be from m equals to 2 to infinity. In this term, if I take the first term, then again the rest of the term would be sum from m equals to 2 to infinity. Here we already have m from 2 to infinity again, and again in this series, if I take out first two terms, I'll be left with the sum starting from m equals to 2. So to make this left hand side uniform, I'll just remove the first few terms in the series wherever required. So this makes our equation. This implies 2c2 plus 6c3x, just taken out the first two terms. Then I'll take out the first term of the second series, c1x. Then for this series, first two terms, 2c0 plus c1x. Rest we have summation m from 2 to infinity m plus 2 m plus 1 cm plus 2 plus mcm plus cm minus 2 plus 2cm times x to the power m equals to 0. Now we'll just simplify this and then compare the coefficients of x to the power m. This gives us 2 c0 plus c2 plus 6c3 plus 3c1 times x plus summation m from 2 to infinity cm plus 2, m minus 2 plus m plus 2 cm, just clubbing these two terms together, plus m plus 1 m plus 2 cm plus 2 times x to the power m equals to 0. Now on right hand side, coefficient of x to the power 0 is 0. This implies c0, let me write it with some other color. This implies c0 plus c2 equals to 0. Again, the coefficient of x is 0. So we get 6c3 plus 3c1 equals to 0, and cm plus 2 is equal to minus cm minus 2 minus m plus 1 cm m plus 2 cm by m plus 1 times m plus 2 for every m greater than equal to 2. This gives us c2 is equal to minus c0, c1 is equal to, c3 will convert all the things in terms of c0 and c1. So c0 and c1 would be fixed constant for us. And then we'll find the value of c2, c3, c4 in terms of c0 and c1. So c3, from here c3 is minus c1 by 2, which implies c4 is equal to minus 4 times c2 plus c0 by 12, which is equal to, what was c2? c2 was minus c0. So minus 4 times c0 plus c0 by 12, which gives us c0 by 4. Therefore, C4 is equal to C0 by 4. Similarly, you can find C5 would be 3C1 by 40 and so on. Now we have a proper scheme. We can find all CMs based on this formula. Therefore, we have Yx is equal to C0 plus C1x minus C0 x square, because C2 is minus C0. Then C3 is minus C1 by 2 x cubed. Then C4 is C0 by 4 x power 4. Then C5. So this was C5. C5 was C0 by 4. Is it C0? It's 3C1 by 4. Please do try to solve all these things yourself. It may happen that I had done some calculation mistake. So don't just blindly follow or accept whatever I have written. Try to solve it yourself. This is plus 3C1 by 4 x power 540 and so on, which can be further. We can take C0 to be common. We get 1 minus x square plus x power 4 by 4 and so on, plus C1x times 1 minus x square by 2 plus 3x power 4 by 40 and so on. So this is a power series solution to the given problem. I hope you all got the concept behind this solution. All we need to see is that, first of all, since we need to find the solution in powers of x, that means we want the solution near x equals to 0. So firstly we'll see whether x equals to 0 is an ordinary point or singular point or what kind of point it is. So here clearly x equals to 0 is an ordinary point. Now since it is an ordinary point, we know that there exists a power series solution near x equals to 0. So we suppose Yx to be this power series. So then we just differentiate it once and twice and then substitute the values of y dash and y double dash in the given equation. Now, because it is a solution, it must satisfy the equation, and then just simplifying the sum. Uh, there might be some confusion while solving this part. I want you all to just try it yourself. Take pen, paper, solve all these things yourself, then compare the coefficients of x to the power m on both the sides. Then using that comparison, we can easily find the values of ci's, taking c0 and first two terms being any constant. So basically these first two terms can be found if we have the initial value. We'll see such questions later. So I hope this was fine. Let's move to the next question. Question 3. Find the power series solution in the power of x minus 1. That means we need the solution near x equals to 1 of the initial value problem. Now we will be solving the initial value problem. In this case, we won't be left with any constant. X y double dash plus y dash plus 2y equals to 0. Y at 1 is 1. Y dash 1 at 1 is equal to 2. Let's number this. system as 1. Solution. So I hope it is clear enough that x equals to 1 is an ordinary point for this problem. I hope I don't need to explain it again clearly. X equals to 1 is an ordinary point. This implies there exists a solution by x of the form by x equals to summation n from 0 to infinity cn x to the power n. Sorry, x minus 1 to the power. So just take the derivative of y, find y dash, y double dash, and substitute those terms, those sums in equation first. I'll wait for 5 minutes so that you can try it yourself. It's just basic calculation. So what do we get? y dash x is equal to summation n from 1 to infinity n cn x to the x minus 1 to the power n minus 1, and y double dash x is equal to summation n from 2 to infinity n minus 1 cn x minus 1 to the power n minus 2. Now after substituting this, we get substituting by y dash and y double dash in equation 1, we get summation n from 2 to infinity n minus 1 cn x minus 1 to the power n minus 2 times x plus summation n from 1 to infinity n cn x minus 1 to the power n minus 1 plus 2 summation n from 0 to infinity cn x minus 1 to the power n equals to 0. Now these two, this one is already in x minus 1 to the power n. To convert this in terms of x to the power n, again we'll do the same substitution. We'll take m equals to n minus 1 and see what these coefficients are. The problem arises in this case because here we have x minus 1 and x. We want this to be in terms of x powers of x minus 1. So we'll see summation n from 2 to infinity n minus 1 cn x minus 1 to the power n minus 2 times x is equal to summation n from 2 to infinity n minus 1 cn x minus 1 to the power n minus 2. Now we can write this x as x minus 1 plus 1, which becomes summation n from 2 to infinity n minus 1 cn x minus 1 to the power n minus 1 plus summation n from 2 to infinity n minus 1 cn x minus 1 to the power n minus 2, which again after substituting, here we'll substitute n minus 1 by m and here n minus 2 by m, we'll get, which is equal to summation m from 1 to infinity m plus 1 cm plus 1 x minus 1 to the power m plus summation m from 0 to infinity m plus 1 m plus 2 cm plus 2 x minus 1 to the power m. And therefore we have summation m from 1 to infinity m plus 1 cm plus 1 x minus 1 to the power m plus summation m from 0 to infinity m plus 1 m plus 2 x minus 1 to the power m plus summation m from 0 to infinity m plus 1 m plus 2 cm plus 2 x minus 1 to the power m plus summation m 2 times m from 0 to infinity cm x minus 1 to the power m equals to 0. Now these two came from here and rest two terms. This one is same, and this one can be written like this after substituting n minus 1 by m. Okay, then now again we have some of this series are from m equals to 1, some are from m equals to 0. We'll make them uniform. So we'll take out first term from this, and this. That is the term m equals to 0. Then we'll be left with the sum from m equals to 1 to infinity. So this implies 2c2 plus c1 plus 2c0 plus summation m equals to 1 to infinity 2cm plus m plus 1 square cm plus 1 plus m plus 1 times m plus 2 cm plus 2 x minus 1 to the power m is equal to 0. Now comparing the powers, the coefficients of x minus 1 to the power 0, x minus 1 to the power 1, x minus 1 to the power m, we get this implies 2c0 plus c1 plus 2c2 equals to 0, and from here we get cm plus 2 is equal to minus 2cm plus m plus 1 square cm plus 1 by m plus 1 times m plus 2 for every m greater than equal to 1. Now here we had the initial condition. Using that initial conditions, we'll find C0 and C1. Now since yx is equal to summation from 0 to infinity, or we'll write it as summation n from 0 to infinity Cn x minus 1 to the power n. Now what was the value at 1? 1 equals to y at 1. Now y at 1 is just C0. Therefore, our C0 is 1. And what was y dash? Y dash x is summation n from 1 to infinity n Cn x minus 1 to the power n minus 1. And the initial condition that we had, 2 is equal to y dash 1, and y dash at 1 is just C1. Therefore, C1 is 2. Now we have C1 and C2, C0 and C1. Using that we can find C2. This implies C2 is equal to minus C1 minus 2C0 by 2, which is minus 2. Therefore, C2 is minus 2. Then rest of the CIs we can find using this relation. So this gives us C3 is equal to minus 2C1 plus 4C2 by 6, which is equal to minus 2 minus 4 C2 by 3, which is equal to 2 by 3. Therefore, C3 is equal to 2 by 3. Similarly, you can find rest of the term. Similarly, we'll get C4 equals to minus 1 by 6. All these are just calculations. You can check it. Just have patience. Write it nicely, properly, take your time to calculate everything. There might be some confusions, and because of some small mistake, you'll end up having wrong answer. So I'll suggest you to stay calm, just calculate. So we'll get C5 equals to 1 by 15 and so on. Therefore, our solution by x is equal to sorry x equals to C naught was 1 plus C1 was 2. So 2 times x minus 1. Then C2 was, what was C2? Minus 2. Minus 2 times x minus 1 square plus 2 by 3 times x minus 1 cube minus 1 by 6 times x minus 1 power 4 plus 1 by 15 times x minus 1 power 5 and so on. This is our power series solution. Let's solve one more initial value problem. Find the power series solution of the initial value problem. X square minus 1 y dash plus 3xy dash plus xy equals to 0 along with the initial conditions y2 equals to 4, y dash 2 equals to 6. Now we are not given the point where we need to find the solution, but we can guess that using the initial condition. Now we are given the values of y and y dash at x equals to 2. So it will be helpful for us only if our solution was in the form of x minus 2 to the power something. So, and also we know that solving or writing summations, all these things near 0 is quite easier as compared to writing x minus 2 to the power something. So we'll just substitute x minus 2 by t. Solution. We'll start with let t equals to x minus 2. This will not affect our equation. Again, we'll have dy by dx is equal to and d2y by dx square is equal to d2y by dt square. So our problem, this implies first becomes x square minus 1, sorry, not x square. Now we'll have t plus 2 square minus 1y double dash plus 3t plus 2 times y dash plus t plus 2 times y equals to 0. And the initial conditions are y at t for x equals to 2, t is 0 is equal to 4 and y dash at 0 is 6. Now let's just simplify this equation. We'll get t square plus 3 plus 2t y double dash plus 3t plus 2y dash plus t plus 2 times y equals to 0 with the same initial condition. Now we'll solve this. Clearly t equals to 0 is an ordinary point for this equation. Equation 2. I hope it is very clear enough to everyone that t equals to 0 is an ordinary point for the differential equation given by equation 2. So y equals to summation cn x t to the power n will be a solution, and then we'll again similarly as done earlier we'll find the coefficient ci's. So let yt equals to summation 0 to infinity cn t to the power n be the solution. This implies y dash t is summation n from 1 to infinity n c n t to the power n minus 1, and y double dash t is equal to summation n from 2 to infinity n n minus 1 c n t to the power n minus 2. Now substituting the values of y dash and y double dash in equation 2, we get summation n from 2 to infinity n n minus 1 c n t to the power n plus 3 summation n from 2 to infinity n n minus 1 c n t to the power n minus 2 plus 2 summation n from 2 to infinity n n minus 1 c n t to the power n minus 1 plus 3 times summation n from 1 to infinity n c n t to the power n plus 6 summation n from 1 to infinity n c n t to the power n minus 1 plus summation n from 0 to infinity c n t to the power n plus 1 plus 2 times summation n from 0 to infinity c n t to the power n equals to 0. Now again, as done earlier, we'll just make the equation more uniform so that everything is in the terms of t to the power m. We'll make required substitutions, and after that our equation becomes, I'll just write it directly. I want you all to just see how the next step comes. It will take time. You'll have to see each of the series wherever the sum is not in the t power in the terms of t to the power n, and then substitute them. This will turn out to be summation m from 2 to infinity n m minus 1 c m t to the power m plus 3 times summation m from 0 to infinity m plus 1 m plus 2 c m plus 2 t to the power m plus 2 times summation m from 1 to infinity m m plus 1 c m plus 1 t to the power m plus 3 times summation m from 1 to infinity m c m t to the power m plus 6 times summation m from 0 to infinity m plus 1 c m t to the power m plus summation m from 1 to infinity c m minus 1 t to the power m plus 2 times summation m from 0 to infinity c m t to the power m equals to 0. Now again, we'll take out the terms so that we have the series from with the sum from m equals to 2 to infinity. So we'll just take out the term corresponding to m equals to 0 and m equals to 1. So this implies 6c2 plus 6c1 plus 2c0 plus 18c3 plus 16c2 plus 5c1 plus c0 times t plus summation m from 2 to infinity Cm minus 1 plus Cm 2 times Cm plus 2 m plus 1 m plus 3 Cm plus 1 plus 3 times m plus 1 m plus 2 Cm plus 2 times t to the power m equals to 0. Again we'll just compare the coefficients of x, x square, x cube and so on. We get, also we had the initial condition. Let's start with the initial condition. Now since y at 0 was 4, we have 4 equals to y at 0 and y at 0 is c naught. Therefore, c naught is 4. Similarly, 6 is equal to y dash 0, which is c1. Therefore, c1 is equal to 6. Now, from here, what do we have? This implies c2 is equal to minus c naught minus 3 times c1 by 3. c2 by 3, which is equal to, what was c naught? 4 minus 4 minus 3, 6, 18 by 3, which is minus 22 by 3. Therefore, c2 is equal to minus 22 by 3. Now, we'll see this sum. This will give us, also we have Cm plus 2 is equal to minus Cm minus 1 minus m square plus 2m plus 2 times Cm minus 2 times m plus 1 m plus 3 Cm plus 1 by 3 times m plus 1 m plus 2. This gives us C4. We had C3. Okay. We have this term also, no? From this, we have C3 is equal to minus C naught minus 5C1 minus 16C2 by 18, which will turn out to be 125 by 27. Just recheck my calculation. There might be some mistake. And this gives us C4 is equal to minus C1 minus 10C2 minus 30C3 by 36, which will turn out to be minus 313 by 18. And so similarly, you can find C5, C6 and so on. Therefore, our yt is equal to 4 plus 60 minus 22 by 3t square plus 125 by C3 was 125 by 27. 27t cube minus 313 by 18 t power 4 and so on. Now what was t? T was x minus 2. So we have yx equals to 4 plus 6x minus 2 minus 22 by 3 x minus 2 square plus 125 by 27 x minus 2 cube, and so on. So this is our power series solution to the given initial value problem. Okay, then let's move to the next question. Question number 5. All the questions have mainly, I think, the same scheme. All you need to do is take a power series, find its derivatives, put those values in the given equation, then compare the, then make the equations uniform in terms of x to the power m, then compare the coefficients of x to the power m. Using those relations, just find the values of ci's. Only if the point where we are taking the series is an ordinary point. So find the series solution of 1 minus x square y double dash y dash minus y equals to 0. Let's number it as 1 in power of x. Again, clearly x equals to 0 is an ordinary point. We'll start with let yx is equal to summation n from 0 to infinity cn x to the power n. Now I want you to calculate y dash, y double dash, put it in the equation and write the series. I'll just wait for 5 minutes. Then I'll tell you what was the series. Sum of the series. So after substituting the value of y dash and y double dash, you'll get summation n from 2 to infinity n minus 1 cn x to the power n minus 2 plus summation n from 2 to infinity n minus 1 cn x to the power n minus 2 summation n from 2 to infinity n minus 1 cn x to the power n minus 1 plus 2 summation n from 1 to infinity n cn x to the power n minus summation n from 0 to infinity cn x to the power n equals to 0. Then further we'll make this equation uniform in powers in terms of x to the power m. We'll get summation m from 0 to infinity m plus 1 m plus 2 cm plus 1 sorry m plus 2 x to the power m minus 2 summation m from 1 to infinity m plus 1 cm plus 1 x to the power m plus summation m from 2 to infinity m minus 1 cm x to the power m plus 2 summation m from 1 to infinity m cm x to the power m minus summation m from 0 to infinity cm x to the power m equals to 0. Again, we'll take out first few terms from the series and we'll get 2c2 minus c naught plus x times c1 minus 4c3 plus summation m from 2 to infinity m plus 1 minus 1 cm minus 2m m plus 1 cm plus 1 plus m plus 1 times m plus 2 cm plus 2 x to the power m equals to 0. Now this gives us C2 is equal to C naught by 2, C3 is equal to C1 by 4, and Cm plus 2 is equal to minus m plus 1 minus 1 Cm minus 2m m plus 1 Cm plus 1 by m plus 1 m plus 2 for every m greater than equal to 2. So this gives us C4 is equal to minus 5C2 minus 12C3 by 12, which would be minus 5C0 by 24 plus C1 by 4. And similarly, you can find rest of the terms C5, C6 and so on. So therefore, our solution by x is equal to C0 plus C1x plus C0 by 2x square minus C1 by 4x cube plus C1 by 4 minus 5 C0 by 24 x by 4 and so on. So we'll just take the terms involving C0 and C1 separately. c naught times 1 plus x square by 2 minus 5 by 24 x power 4 and so on, plus c1x times 1 minus x square by 4 plus x cube by 4 and so on. This. So this is our solution. Again, we have a similar question. We need to find the power series solution for y double dash minus x y dash plus 2y equals to 0. Here, x equals to 1. Again, we'll start with the substitution t equals to x minus 1 and find this power series solution in terms of t power m. Let t equals to x minus 1. Then our problem becomes y double dash minus what was x? X is t y dash plus 2y equals to 0. Clearly t equals to 0 is an ordinary point for this problem. Let me number it as 1. Again we'll take yx by t. Since t equals to 0 is an ordinary point, therefore yt equals to, there exists some power series solution to differential equation 1. We'll take yt equals to summation n from 0 to infinity cn t to the power n. Now again, please calculate y dash, y double dash, substitute it in equation 2 and find the equation. So finally we'll get, I'm just writing it directly, please calculate it yourself. All these are just basic calculations. We'll get 2c2 minus c1 plus 2c0 plus summation m from 1 to infinity to minus mcm minus m plus 1 c m plus 1 plus m plus 1 m plus 2 c m plus 2 times t to the power m equals to 0. Which implies c2 equals to c1 minus c0 2 c0 by 2, which is c1 by 2 minus c0 Further, we have Cm plus 2 is equal to m plus 1 Cm plus 1 plus m minus 2 Cm by m plus 1 m plus 2 for every m greater than equal to 1. This implies C3 is equal to 2C2 minus C1 by 6, which is 2, sorry, 1 by 3 times C2. C2 is C1 by 2 minus C0 minus C1 by 6. Which is minus C0 by 3. Similarly, you can find C4, C5 and so on. Therefore, our solution y in terms of t is C0 plus C1t plus C1 by 2 minus C0 t square minus C0 by 3t cube and so on. Now what was t? T was x minus 2. Therefore yx is equal to C0 plus C1 x minus 2 plus C1 by 2 minus C0 x minus 2 whole square minus C0 by 3 x minus 2 whole cube and so on. Let's just write terms involving C0 and C1 separately. We get C0 times 1 minus x minus 1. Oh, what was our point? T was x minus 1. I'm so sorry. This is x minus 1. X minus 1, x minus 1, x minus 1. So this is x minus 1 square minus x minus 1 cube by 3 and so on plus C1 times, let's take x minus 1 as common, we get 1 plus x minus 1 by 2 and so on. Therefore, this is our function yx, solution to our given problem near x equals to 1. Let's move to the next question. Question 7th. Express the polynomial x square and x power 4 minus 3x square plus x in terms of legendary polynomial. So first of all, we should know how our legendary polynomial is given. So we have p0 x is equal to 1, p1 x is equal to x, p2 x is equal to 3x square minus 1, p3 x is equal to 5x cube minus 3x by 2, p4 x is equal to 35x power 4 minus 30x square plus 3 by 8. All these pn's are called legendary polynomials. Now we'll try to write our polynomials x square and this polynomial in terms of the legendary polynomial. So clearly we have the term x square in p2x. So we can write x square is equal to p2x plus 1. So p2x plus 1 is 3x square. We'll divide it by 3. We'll be left with x square. This p2x is actually p2x is 3x square minus 1 by 2. So we need to multiply this p2x by 2 here. So this is our x square. Now next polynomial is x power 4 minus 3x square plus x. Now see, x power 4 is given in p4. So we'll just take 8 times p4 will give us something of the type 35x power 4 minus 30x square plus 3. Now we want to eliminate this minus 30x square plus 3. So we'll just write plus 30 x, and what was x square? X square was 2p2x plus 1 by 3, and then we have minus 3 by the numerator is now 35x to the power 4. We want just x to the power 4, so we'll just divide it by 35. Now next term is 3x square. So minus 3, and what was x square? 2p2x plus 1 by 3, and what was x? X is p1x plus p1x. So let's just simplify it. We'll get 8p4x plus 20p2x plus 7. 7 times 1. And since 1 is p naught x, we'll just write it as 7 p naught x by 5 minus 2p2x plus p naught x plus p1x. Now this is 8p4x by 35 minus 3 by 7 p2x. Just simplify this. 20 by 35 is 4 by 7 minus 2. 4 by 7 minus 2 would be 3 by 7. We have 4 by 7 minus 2 would be minus 10 by 7. So it's minus 10 by 7 p2x plus p1x, and rest of the term is minus 4 by 5 p naught x. It's a humble request, kindly check my calculations again. There might be some mistakes because there are so many calculations. There might be some minor mistake which would have made me end up with a huge difference. So it would be better if you do all these calculations by yourself with pen paper. So this is our x power 4 minus 3x square plus x in terms of legendary polynomials. So let's move to the next question. Question 8. Prove that the 2k and 0, this Pn is again the legendary polynomial, is equal to minus 1 to the power k 2k factorial by 2 to the power 2k k factorial square. Solution. Now we know that for every mod x less than equal to 1, we have summation n from 0 to infinity z to the power n. Pnx is equal to 1 minus 2xz plus z square to the power minus 1 by 2 for all mod z strictly less than 1. So this gives us that summation n from 0 to infinity z to the power n at 0 is equal to 1 plus z square to the power minus 1 by 2. Now for mod z less than 1, we can expand this and we have summation n sorry n from 0 to infinity minus 1 by 2 minus 1 by 2 minus 1 minus 1 by 2 minus 2 and so on up to minus 1 by 2 minus n minus 1 times z square to the power n by n factorial. You all must be aware of this expansion. So let's just simplify it. We'll get summation n from 0 to infinity minus 1 to the power n, because we have n times minus. Then we have 1 by 2 3 by 2 5 by 2 and so on up to 2n minus 1 by 2 times z to the power 2n by n factorial. So these are n terms. We'll get summation n from 0 to infinity minus 1 to the power n 1 into 3 into 5 and so on up to 2n minus 1 by 2 to the power n times n factorial z to the power 2n. Now we'll just to make this numerator term as 2n factorial, we need the in between terms 2 4 and so on. So we'll just multiply by those things and divide by those numbers. So we'll get is equal to summation n from 0 to infinity minus 1 to the power n. So we'll get 2n factorial z to the power 2n by 2 to the power n factorial, and rest of the terms were 2 into 4 into 6 and so on up to 2n. So again I'll just take 2 common from all these terms. So I'll be taking out 2 to the power n, which gives us summation n from 0 to infinity minus 1 to the power n 2n factorial z to the power 2n by 2 to the power n and again 2 to the power n. So 2 to the power 2n n factorial and again n factorial square. So therefore, what do we have? Summation n from 0 to infinity z to the power n Pn0 is equal to summation n from 0 to infinity minus 1 to the power n 2 to the 2n factorial by 2 to the power 2n n factorial square times z to the power 2n. Now I'll be again comparing the coefficients of z to the power 2n, z to the power 2k, will get, so equating the coefficients of z to the power 2k, will get p2k at 0 is equal to minus 1 to the power k 2k factorial by 2 to the power 2k k factorial square. This is what we wanted. Hence we are done. Okay, then let's move to the next question. Prove that integration minus 1 to 1 x times pn minus 1 x dx is equal to 2n by 4n square minus 1. We'll be using the following two results to prove this. First one is, let's just recall. We'll be using the same results in next questions as well, so it's better to recall. We have x pn x is equal to n plus 1 by 2n plus 1 times pn plus 1x plus n by 2n plus 1 pn minus 1x, and the second one is integration minus 1 to 1 pmx times pnx is equal to 0 if m is not equal to n. This property is called orthogonality, and it is equal to 2 by 2n plus 1 when m is equal to n. So by first we have pnx times pn minus 1x is equal to, I'll just multiply the right hand side by pn minus 1, so we'll get n plus 1 by 2n plus 1 times pn plus 1x pn minus 1x plus n by 2n plus 1 pn minus 1x whole square x times. So this gives us integration minus 1 to 1 x pn x times pn minus 1 x is equal to, now this integral of this term will be 0 because n minus 1 is not equals to n plus 1, 0 plus, this is just a constant, n by 2n plus 1 integration minus 1 to 1 pn minus 1 square x, which is n by 2n plus 1 times, this here in result 2 will be replacing n by n minus 1, so this is 2 by 2 n minus 1 plus 1, which is 2n by 2n plus 1 times 2n minus 1, which is 2n by 4n square minus 1, which is what we wanted to prove. Let me write it properly. Oh, okay, it's n 4n square. Integration minus 1 to 1 x pn x This is our required result. We'll be again using the same result first and second to prove next question. So let's move to the last question of this assignment, this tutorial, sorry. Prove that integration minus 1 to 1 x square pn minus 1 x times pn plus 1 x dx is equal to 2n n plus 1 by 2n plus 3 2n minus 1 2n plus 1. Solution. Now by first we have first we have x pn minus 1 x is equal to n by 2n minus 1 pn x. I'll be just replacing n by n minus 1 in equation result 1 plus n minus 1 by 2n minus 1 pn minus 2x, and now I'll be replacing n by n plus 1 in the result 1. So we'll get x times pn plus 1x is equal to n plus 2 by 2n plus 3 times pn plus 2x plus n plus 1 by 2n plus 3 times pn x. Let's just multiply these two equations. We'll get x square pn minus 1x times pn plus 1x is equal to or in fact it would be more easier if I write it as x square 2n minus 1 2n plus 3 times pn minus 1x pn plus 1x is equal to n pnx plus n minus 1 pn minus 2x times n plus 2 pn plus 2x plus n plus 1 pnx, which is equal to n plus 2 pn plus 2x pnx plus n plus 1 pn square x plus minus 1 n plus 2 pn minus 1x pn plus 2x plus n minus 1 n plus 1 pnx pn minus 2x. Now I'll just integrate both the sides from minus 1 to 1. We'll get 2n plus 3 2n minus 1 integration minus 1 to 1 x square pn plus 1x pn minus 1x is equal to, all integral of all these terms would be 0. We'll be left with n plus 1, and integral of this using result 2 will get this is 2 by 2n plus 1. 2 by 2n plus 1. Therefore, minus 1 to 1 x square tn plus 1x tn minus 1x dx is equal to 2n n plus 1 by 2n minus 1, 2n plus 1, 2n plus 3. This is the required proof. I hope all the steps were clear enough. This today's tutorial session was mainly based on calculation. There it wasn't much of analysis. All you need to do is practice these calculations. It would be I am again telling you all to just practice all these questions again and again so that you won't get any kind of calculation mistake. Those silly calculation mistake would end up you into very disastrous situation. So I'll just suggest you to solve and try these questions with your hands. So I hope today's session was fine. If you have any kind of doubt, please let me know through email or comment on YouTube video. Okay then, thank you.